नहीं, ये निकाल के रख देता हूँ. हेलो. थैंक यू. हो गया? सेट? ऑल सेट? Because as far as my analysis is concerned, we people are delayed with 1 hour with our session. Means you may not feel, but this is my personal feeling. Okay. So anyways, we will have to just cover the things. So a gear will be shifted. Okay. Now not on second gear or third gear, है ना? It's on now top gear. It's okay. So just please, but no need to be worried. I am with you, है ना? And I'm letting you know this thing also. So just please be prepared with your mind. I would make you all comfortable, है ना? In all sessions. Should we proceed? Okay. So now, look. Installation done. One more time. Installation done. Google Colab run done. I will also demonstrate. Don't worry. है ना? Followed to that one. Jupyter Notebook. On Jupyter Notebook, you run the code. Clear? I will also demonstrate that how to run on dedicated machine. Clear? Few of the people done already. It's okay. Now you look at here. This is the execution of our Qiskit codes on different environments. Okay. So now this code actually ran on two different environments. This is first one is showing a simulation. Okay. For which I have already shared you the code. You people have run that code. Yes, successfully the code is executed at your machine. Clear? And you people are also obtaining the results. Okay. Now you try it. It's the time to analyze what we people are getting as per our expectations. Okay. So this is the simulation code, and the right hand side part, what you may be able to see, this is a real IBM quantum machine experiment. Clear? So what happened here? This is the simple simulation of a Hadamard gate, means to demonstrate the superposition, what we discussed here. Clear? So by putting a Hadamard gate here, after we applied the measurement. So what Hadamard will do? It creates the superposition. Now which superposition? This is important. I told you two types of superposition can be created. One is uniform, second is non-uniform. Uniform and non-uniform means what? The quantum states would be associated with same probability amplitude, like equal probability distribution. Yes or no? Otherwise, your quantum states will realize different probability distributions. I gave you the example, like here in this case, the probability distribution with associated to what? Quantum state 0 and 1, both is 1 by 2, that is 50% chances. Okay, but if we see what the other coding mechanism, like a 0 state have been encoded with suppose 25% chance, and 1 state is encoded as suppose 75% chance. So there is a possibility, I will let you know in tomorrow's when like machine learning session, okay, that why these amplitudes can be differently encoded. So now here you look, this is the simple circuit. I have created this circuit, shared you the file, you people have already executed the circuit, and you checked out of 1024 runs of the same circuit, Here in this random experiment, 502 times I observed what? 0. 522 times I observed what? 1. But it does not remain same for every execution. I think you must have observed this thing. Yes or no? At each execution, your parameters, your values of obtaining a quantum state as 0 or 1 keeps changing. Yes or no? It happens. Why? Because the machine is probabilistic in nature. So what is the analysis here? That the probability to measure the answer either as 0 or 1 is half. Okay? So at each iteration we can get our quantum state as 0 or 1 with half probability. Okay? Now we run the same experiment for 1024 time, and out of 1024 time we are just analyzing that how many times 0 and 1 got occurred. Understood? I told you, and few of among you have already tested, that sometimes you are getting 450, 550, okay, like 490, 510, like these. So every time it keeps changing. Clear? So what does it mean? Every time at each executional iteration the quantum state gets created, okay, by applying Hadamard. Quantum state gets created, and when we apply this what? Measurement, your quantum state is lost, and you measure your classical outcome. Understood? Once you have done like this, you are going for next iteration. Similarly, you have done how many iterations? 1024 iterations in order to analyze your results. But there is no noise. Why? Because it's a simulation. You are running your code on your local machine. Understood? Now look, here the same results. This is the circuit. The circuit to be created on IBM Quantum. Okay, this is the corresponding COSM code, assembly code. I told you this must be there on the right hand side of the tab. Okay, and these are the simulation probabilities. And look, because this code has not been run, this has not been run yet, so what it is showing? 0. It's a default state, because I did not set this code to run. You look at here, it is written like setup and run. Understood? So once we click on this button, the same circuit will be switched to what? To the dedicated quantum machine, and that machine will run this circuit, and the output will appear to our client machine. Understood or not? Now after that one, but if you observe, still the number of times 0 and 1 are appearing in just close proximity. Yes or no? There is close proximity to just get a resultant as 0 or 1. Now this is the code has run, that is the same code what we were talking about, this code, okay, like this code. So the code has run here, so this 0 and 1 are appearing almost for nearby times, that is more than or around 500, and this code is run on, this is the quantum processor name, this is the name. I think you may not be able to see, it's written as IBM Sherbrooke. Actually what happens, it's the resources available on cloud, so the people used to give logical names to their servers. So the quantum machines are assigned with some logical names. So one of the logical name here is IBM Sherbrooke. I run that circuit on this machine. Okay. So that backend I used while running my circuit. Understood? But after running this circuit, there is no problem, because 0, 1 was the expected one, and only we measured what? 0 and 1. No problem. Now you look at what happened. Okay. Now you look at entanglement. This is the next. Okay. Now look at here. This is the circuit of entanglement. Hadamard followed by C0, followed by measurement of each qubit. After measuring that qubit, okay, we have measured that like 0, 0 and 1, 1. Only these two states are appearing or not? Like this. Okay. 0, 0 and 1, 1. There is no such possibility of other states. Clear? Like here, but if you see the same circuit, if I set up and run on the quantum machine, So it is showing like 0, 0, 0, 1, 1, 0 and 1, 1. It is showing now, but I have not executed this one. But when I used to execute, you look at here, when I executed, this is the number of instance 0, 0 and 1, 1 was measured. Clear? But unexpectedly, we are measuring what? 0, 1 and 1, 0. So actually we did not have any measurement apparatus in order to measure 0, 1 and 1, 0, because we have set our quantum state as 0, 0 plus 1, 1 by root 2. So how come it is possible? Yes or no? So how it is possible? Just because of the noise remains present in the system. So due to the noise, these two arbitrary random quantum states are measuring. Clear my point? And this chance of error will always remain within our quantum system. Understood? But no need to be worried. I told you in the last session that almost with 99% of accuracy you will get the correct result. Understood? Yes? So now look. Now come on to the that is revisiting to all things. Come on, fast. Hai na? Because based on these things we will be just proceeding with our codes. Okay? So now look at here. This is an identity gate. We know how to get the identity gate. Any matrix operator be designed using what? Outer products. Yes or no? There are three products you should be aware of. The first product is inner product. Okay, inner product means, how do we write inner product? Inner product means bracket system. Understood? Inner product means bracket system. It is basically used for measuring our answers. Understood? Second is tensor product. Tensor is to expand our quantum system over the higher dimensional Hilbert space. Yes or no? So for that one we use cat system. Like I wrote down like this, na? This is what? This is the tensor of 0 and 0. So we can combinedly writing it as 0, 0. Understood? Their corresponding vector would be like. Understood? Now other is outer product. Outer product means cat followed by bra. So now in a inner product, what is the size of the outer product? Sorry, that is the outcome. 1 cross 1. Almost. Yes or no? We get the computational result as 1 cross 1. If you write bracket, so bra size is what? 1 cross 2 raised to the power n, and cat size is 2 raised to the power n cross 1. Inner order same, outer order matrix you will get, that is 1 cross 1. Yes or no? That is why you may expect the classical outcomes. Understood? What about tensor? If 2 cross 1, tensor with 2 cross 1, it would become 4 cross 1. Again tensor with 2 cross 1, so 8 cross 1. Clear my point? So if you are dealing with n qubit system, so there would be 2 raised to the power n cross of 1. That would be the size of your tensor product. And in outer product, especially what we started in the early morning session, what we discussed, this cat followed by bra. Cat, how do we write? 2 raised to the power n cross 1. And bra we write 1 cross 2 raised to the power n. So inner order is 1, 1. So outer order matrix would be 2 raised to the power n cross 2 raised to the power n. So that is why that matrix operator is compatible to work on for certain transformation purpose over the quantum vectors. Understood or not? Is it clear? Huh? So now, so you have a quick look again. So this is the I, this is the outer product. Yes? So when we take the outer product of 0, 0 and 1, 1 with plus notation, so you will get this matrix operation, and this is your identity matrix. Understood? Okay, I think you people have already learned it. These all things you people have learned. I am only recalling because we have to discuss on the program aspects. Clear? Now another is for the poly matrices like X, Y and Z. This is X. What this X is doing? Poly X, poly Y and poly Z. No, it's not rotation. Now listen. Viewpoints may be different. I am just letting you know again the shortcut. है ना? One shortcut I discussed to create this what? The quantum state. That is to write with the index positions. Understood? Second thing is, you remember that X applies bit flipping operation. What it does? Bit flipping means if you apply the X operator onto 0, so it becomes what? 1. So 1 means what? 0. How do we write 0? 1 0. So what the resultant you will get? 0 1. It means bits are flipped. 1 becomes 0, 0 becomes 1. Understood? Followed by X. I did not write Y. Otherwise you will be having certain confusion again. So try to remember these things in an order like X, Z and Y. So X is for bit flipping, Z is for phase flipping. What it is for? Phase flipping. Okay. So phase flipping means if your quantum state is ready with 0 and you are applying Z gate, there is no impact on the quantum state. Okay, if you recall. But if your quantum state is what? 1 and applying Z gate, so the phase factor of minus would get added to that state. Understood? Clear? Now the third is what? Y. So Y is responsible for bit flipping as well as phase flipping both. Clear? So means these bits would be flipped as well as phase of a qubit would also be flipped. Not to be called as qubit, quantum state would be flipped. Understood? So these are the terms through which, and these are the matrices. Okay, this is 1001, this is identity, this is X gate, this is Z gate, and this is Y gate. Okay. Now this is a transformation of Hadamard. How do we get this Hadamard? This is a generalized equation in order to write the Hadamard state. Okay. You take two variables because it's a single qubit gate, works on two different aspects. So I have taken two variables here, X and Y, both belongs to what? 0 and 1, that is a bit string. Okay. So now 1 by root 2 of minus 1 raised to the power of X multiplied by Y, cat followed by bra of Y, cat X followed by bra Y. So when you just apply the values of X and Y here, for 0, 0, 0, 1, 1, 0 and 1, 1. Yes or no? So for 0, 0, 0, 1 and 1, 0, you will add no problem. But when you put it for 1, 1, so this function will be evaluated to 1 because rest for all times it would be 0. Yes or no? Like X and Y, if X value is 0 or Y value is 0, okay, or both are 0, so this function would be something raised to the power 0, means it would become 1. Okay. But when it becomes 1, 1, so this minus phase factor would be included here. It is mistakenly plus written here. Clear? So it should be minus. Understood? This phase should be minus. Here it is updated. Clear? Is it clear? So this should be minus here. So 1, 1 should be available with minus phase factor. So once you go or done with this outer product notation forms, you will get these all values. So after getting these values, this is the final or resultant Hadamard matrix. Okay, for which we need not to bother upon, only we need to apply this Hadamard operator. And Hadamard operator takes care of putting your quantum state to a superposition of quantum states. Yes or no? Initial quantum state should be there. Like just let me ask you, on 0 we applied Hadamard. What did we get? 0 plus 1 by root 2. But if my initialized state is 1, then? Yes, sure. So it becomes minus. Like we discussed, no? This is the minus state. Okay. So once, are you there at the plus state or minus state? That is the again thing to be discussed. Clear? Okay. Now, these are some results to be always remember. And we will use these all in Grover search algorithm. So just remember, at that time I will ask you to recall. Okay. Now listen, Hadamard to be applied on 0, this is the state equivalent to plus. Hadamard applied on 1, 0 minus 1 by root 2, this is equivalent to minus state. Clear? Now, Hadamard on plus means you have applied Hadamard on 0, again applying Hadamard. Means it should return back to again the original quantum state. So this is the original quantum state. Okay? Hadamard on plus, you are getting 0. Hadamard on minus, you are getting 1. Is it clear? Now followed to that one, this is the very important operation. What it is? Hadamard x Hadamard. So when you write these three operations in sequence, it is equivalent to what? Z. Z means phase flip. Would you remember? Huh? Just please remember, because this is very important setting in Grover's algorithm. So because at that time when we reach to Grover's algorithmic part, there would be a huge circuits. Okay, long length circuit we will be creating. So once we reach to the long length circuits, the fundamental elements of that circuit we should be well known. Understood? Otherwise, confusion. Okay. So now here, Hadamard followed by x followed by h would be z. Similarly, Hadamard z Hadamard would be equivalent to h. Clear? Is it clear? Okay. So now this is the phase gates. These are phase gates. So the generalized representation of the phase gates I have written down here, that is the matrix operator be written as 1 0 0 e raised to the power I theta. That is the Euler's formula. Yes or no? Because anyways my particle is following the wave like nature. Clear my point? So just because of that one, we have to just be known about the certain position. Okay, so for that one, we are just evaluating that Euler's formula, and it e raised to the power I theta becomes cos theta plus of I sin theta. We need to define only the value of the theta here. Okay, so now if we put the theta as pi, okay, so if the theta is put as pi, so it would become e raised to the power I pi. Okay, and e raised to the power I pi means cos pi I sin pi. So cos pi means minus 1, and this would be sin pi would be 0. Yes or no? So at that time, the matrix would become what? That is minus 1, because this whole evolution of e raised to the power of I theta is becoming as minus 1. So this is minus 1 we people are getting at z gate. This is the hidden facts through which we people are obtaining our z gate. Clear? Now another is put theta as pi by 2. Now come down like pi by 2. So at pi by 2, e raised to the power I pi 2, it would become what? That is cos pi by 2 plus I sin pi by 2 is equal to what? That is 0 plus I1. Okay, iota 1. So this time e raised to the power I pi by 2 would be evaluating to I. Okay. So this is the basic representation of what? S gate. And you remember this gate, I would demonstrate these gates like S, Z and T on quantum phase estimation. This is one of our expected lecture. Are yes or no? Do you know the topics to be covered? Huh? So the topics means one is related to quantum amplitude amplification. That is Grover's search mechanism. So whatever I am just asking you to remember, just please remember. Otherwise you will be in a trouble. Understood? So these all gates, Z, S and T, we require these all. Okay? Because we need to estimate a phase. Phase means this information about the angle theta. Okay? So if you remember the corresponding gate operators, so it would help you a lot. Understood? So Z means theta is pi. E raised to the power I pi is minus 1. S means e raised to the power pi by 2. I pi by 2 means it is evaluated to I. And T gate is pi by 4. So like this pi by 2, pi by 4. So when you evaluate this pi by 4, so you will have e raised to the power I pi by 4. Clear? Okay. Now these are some rotation gates. Okay. like earlier who was these are the rotation gates, okay. Still these are the single qubit rotation gate, and it is to be written as onto the x-axis, y-axis and z-axis. These are the rotations with angle information of theta. So based on angle information of theta, the x, y and z rotations would be applied. So the corresponding matrix operator would be written as directly that Rx of theta, that is e raised to the power minus of theta by 2 of x, where x is the Pauli operator. Basically it is represented using in terms of the Pauli operators, okay. So the Pauli operators would be clubbed here in a rotational form. The same x, y and z. If you see here this x, so means here x is involved. If y, so here y is involved. If z, so this z is involved, okay. And their corresponding matrix operations have become like this. That is cos theta by 2 in diagonals, and minus I sin theta by 2 and minus I sin theta by 2 here, okay. This is as per the evolution of these gates. I will also discuss the same gates when we apply these operators through program. Okay, we will initially apply the gate, we will check what happened, okay. Based on that one, we backtrack to this slide, okay, and at that time you need to calculate through the matrix operation and check whether the transformation what you were expecting, the same is happening here in the system or not. Understood? Okay. Now, so this is these are what? The Rx, Ry and Rz gate and their corresponding matrix operations. And remember, it is what? Single qubit gate. So the operational size of the matrix would be 2 cross 2. Actually 2 cross 2 we usually write, but it is 2 raised to the power 1 cross 2 raised to the power 1, because it's a 1 qubit of gate operator. Clear? Yes? So okay, so let's move. Now multi-qubit gate, we know this is the control NOT gate, you people are known. But now I am about to have some analysis again. This is the operator matrix. How many gates are required for, how many qubits are required for C0? 2. One is called as control qubit, second is called as target qubit. Understood? So for 2 qubit operator, the size of the operator would be 2 to the power 2 cross 2 raised to the power of 2, means 4 cross 4. So it's a 4 cross 4 operator. But the fact what you may realize here, this is the NOT operator we have applied. Yes? Just please look at the slide. This is the NOT operator we have applied on the target. If you closely observe this submatrix of 2 cross 2, what is this? X gate. So it is showing what? It is indicating that this is basically a controlled NOT gate. Understood? Now, and we know the operational significance of this gate, okay. This is used for the XOR purpose also. Now this is control Z. So still the operator size would be 4 cross 4 because of the 2 qubit gate is there. So for 2 qubit gate, 4 cross 4 would be the size of the matrix. But if you see again, look at here, what is this sub 2 cross 2 matrix? It is Z gate. Understood? So this is how you may you may only remember the operators. Okay, rest of the entries should be 1 in diagonal, nothing else. But the operator you can directly be able to write, nothing to be just to remember in other ways. Okay, so this is control Z. Now followed to control ZS. So for control S, you look at here, this is S gate, this is control S operation, and you remember this control S, control Z, this would be used in what? Quantum phase estimation routine, where a task would be assigned to estimate the unknown phase theta that is contained within the quantum system. Means the things what we are not known, but we are approaching to get the values related to the unknown phase. That would be the objective of that quantum phase estimation. There would be a complex mathematics involved in a phase estimation as well as amplitude amplification. Okay, so slowly we will be gradually we will be moving around. Okay, so is this fine? Next, this is C naught, okay, my CC naught, that is Toffoli gate, okay. It's a 3 qubit gate. 2 qubits are taken as control. When they both become 1 1, we apply what? The NOT operation on the third qubit. I have no interest in just showing these symbols. I have only the interest to show the 4 cross 4 submatrix. Okay, this is C naught followed by 2 cross 2 submatrix. Rest of the diagonal entries 1. So, just because of certain analysis, you may be able to write down the operators directly. There is no such problem. Yes or no? Clear my point? Now, the thing is quantum swap gate. This is important again. The swap gate is having own significance in quantum machine learning part. Okay, like when we perform the kernel transformations. Okay, so for kernel transformations again we have to just relocate the positions of our points from one dimension to other higher dimensions. Clear my point? So again this swap gate would be working there. I will let you know that how it would be fruitful there. Now AB, when you have the quantum state as AB, so it would become BA. So this is the swap gate operation. This is the swap gate. Okay, this is the swap gate operation. If you observe this swap gate, this is what? If you see 0 0, so it is 0 0, but it is not 0 0. It is what? It is 1 0. What about this? It is 0 1, and this is 1 1. So only 0 0 1 and 1 0 have been shuffled. Clear my point? Huh? Like we discussed here, na? This is these two. These two have been shuffled in what? In a swap gate. Clear? So this is the swap gate operation, and you may check that swap, because if both of these qubits have been initialized to same, so you will not get to know that whether something is happening or not. So we have to assign one of the qubit as to be other values. So like this, the Q1 have been assigned as 1. So means what? This is becoming 0 1. This is LSB. That is least significant bit. Okay. So this is LSB. So now this is 0 1. So when you apply this swap gate, this would become 1 0. Understood? Now the similar fact is this is controlled swap gate. Okay, and you will need this controlled swap gate in swap test again. Okay, there would be a specific test. I'll let you know in tomorrow's session. Okay, so when you work with the swap test, so this code of or this circuit would be still needed. And if you observe their corresponding submatrix, so you will get the swap matrix. Clear? Yes or no? Now, these are some quantum designs of the classical gates. Have you worked in earlier sessions for the classical designs or quantum design of the classical gates? Have you worked? I'm just asking. Not all means a few of the classical gate designs. Which one? Only not. So not to directly available now. what to just have a design in that one? It is simple one. If it is there a NOT gate, you apply a NOT operator here. Okay. If you have the quantum state 0, it would turn down to 1. If you have the quantum state 1, it would turn down to 0. There is no such significance. Yes or no? But if I ask you, this is my question to all the faculty participants, if I want to replace this NOT gate, I do not want to design this NOT gate with NOT operator, then can you be able to propose any mechanism? I discussed. Whatever I will ask, the things must have been discussed in the lecture sessions. This is guaranteed. Can you let me know? I asked you to remember. Dekha? What I told? That time I told. Remember. I told remember. This is without X. Without X I could design what? That is a NOT gate. Clear? Okay. Let's move ahead. Now this is the AND gate design. AND gate design. What operator I used? Toffoli. Only by taking Toffoli, the AND gate is applied. You just realize here, I am assigning both of them as 0, 0. So at 0, 0, there is no impact on this one. So just visualize your AND gate truth table. Okay. So truth table, accordingly truth table output is 0. Clear? Now assigning 0, 1 here. So 0, 1 for both of them is still no impact. So still output is 0. For 1, 0 also 0. But for 1, 1, they both will become 1 and taken as control, the output will be flipped. So it is a demonstration of what? Which gate? AND gate. The classical AND gate design using quantum circuits. Clear? Now another is which one? What about NAND? NAND is inverted AND. Yes or no? So we have just applied a NOT gate after AND operation. Now check for OR. Check for OR. I have designed this OR operator using 2 C0 gates and 1 Toffoli gate. I do not say that whatever I am showing you is the best optimal design. This is one of the possible designs. Understood or not? You may have another possible designs. Clear? But can you be able to realize? Just check it here. If we assign 0 here, 0 here, both are 0. So in that case, nothing would be selected and there is no operation on this one, so output would be 0. Clear? Agree? Now, here LSB is 0, this one is 1. So 0, 1. In the case of 0, 1, so at the upper qubit wire there is no impact. But what about this? Because this is 1, so from this one is taken as control, this would be flipped. Clear? And only this one flipping operation, due to this one flipping operation, the output remains 1. Clear? Okay. Now come down to 1, 0. So for 1, 0, if this is 1, this is 0. So for this line there is no impact. And it assures that there is no impact of CC0 operation also, because one of the qubit is already assigned to 0. Okay. So only because of this one, this would be taken as control and it would be applied on the target. Again your outcome is 1. Sure? Can you be able to visualize, or do you need that demonstration on the board? Needed? Just how many people needed? Just raise your hands. Just don't be shy, just please raise your hands. Means now I have one philosophy here to discuss. If you people have come here, okay, means for which purpose? What's the purpose here? That is to learn something. And I know that to teach a teachers is really a rigorous task, because we people are already trained. There is no such acceptance of others' knowledge. Clear? So only a suggestion from my side, when being a teacher, because I am also a good learner, I try to become a good learner. So when I go for any one sessions, so I feel myself as an empty bottle. Empty bottle means the water can be poured inside that one. If you have already have a filled bottle, completely filled, and if I just drop what? Water, at least a droplets, it would start overflowing. Clear my point? So this is suggestion. Just please don't be shy. Do you need? Anyone? Oh, चलो आओ फटाक से देखते हैं. Actually, I observed a few faces, so that is why. Chalo, it's okay. So this is what? 0, 0, and this is 0. What was the circuit? This is the circuit. Okay, this is the first C0, this is the second C0, and this is the Toffoli gate. That is to be written. Correct? Correct? So let's have. This is 0, 0. 0 0. So on 0 0, no wire will be picked up, so this output would remain 0. I think it is clear. Now let's have another. This is 0 and 1. So with this 0, there is no usage of these wires. Every qubit is wire, okay? So there is no usage of this wire. Now this one, by this one, this would be taken as control, okay? And because of this control, this would be flipped. So now at this instance, this 0 would become flipped. Yes or no? So now this would be flipped to 1. Is it clear? There is no impact of other operations. So anyways, for 0 1, we are getting the output as 1, okay? Now let's assign it to 1 0, and this is 0, okay? Assign it to 0. Now for 1 0, for this 0 there is no problem, and for this there is no usage because it's a CC NOT gate. Only with this 1, again this flipping operation will be performed on this 0, so this 0 will become 1 here. Clear? So now again we are getting the output as 1. Sure? Okay? Now the last one is tricky here, like if you see that 1 1 and it is assigned to 0. Now every operator will work. Now first let's go from left to right. This is working. It is initialized to 1. So what it will do, because of this control qubit, it applies the NOT operation on this. So this would become what? 1. Clear? Now the circuit is moving again. Now because of this one, again a NOT operation would be performed here. It becomes 0. Now because they both are 1 1, yes, so again the NOT operation would be performed on this one. Now on 1 1, we are getting our resultant as, I think understood? Fine? Chalo, let's go. So what about XOR? What about this? No, NOR. This OR is done. What about NOR? Apply the NOT gate. And if you want to make it as a complex circuit, so you know that NOT can be replaced with H, Z and H. So you may apply here. Clear my point or not? There can be several possibilities. Now here, what about this XOR? Is it doing XOR? Is it doing XOR? You check by your own. XOR means for different the output is 1. For same output should be 0. Done? No, I did not ask you to check over there, hai na? My question was, he is still here, okay? Have you done with NOR? Oh sorry, XOR? XOR done? All done? Can you be able to realize? Now, XNOR applying NOT. Now look at here. I am asking you all to just work out on your notebook what operational things this circuit is doing. Just check it. We have discussed, don't worry. You know the gate. Know the gate. Just do it fast, hai na? I already told you the gear of our that is session is changed. Running at top gear. Already late by 1 hour actually. Sir, just please do not sit idle, okay? Sir, sleepy? देख के नहीं होगा सर, कर लो. देख के भी हो जाएगा, but it takes practice. XOR. Anything else? Anyone? Achha, let me give you the hint. This is the operator you see, you saw already. क्या है ये? अब now you check whether this circuit is swapping or not. This circuit is equivalent to each other or not, you check. You need to verify. Huh? How do we check? How do we check? Look. If you initialize 0, 0, is there any impact to see? No problem, okay. But if you initialize it to 0, 1, so output should be 1, 0. Okay? Or otherwise if you क्या हो गया यार? Do we have other marker? No, here, please. If you take here 0, this is 1, so the output would be 1, 0 as per the swap gate. So let's pass 0, 1 here. 0, 1 if you are passing, no impact. But with this 1, this would be taken as control. This would be flipped. So this 0 would become 1. And here, what about? This is what? This 1 is going on. Huh? So, but listen, at which instance it becomes 1? This instance. This is the part of the circuit. You divide this circuit first. When I apply 1 here, so with this control, this becomes 1 from 0 to 1. Now this 1 is flowing in this qubit. So when it reaches to this instance, okay, this 1 would be taken as control and this would be flipped again. Clear? So if this would be flipped, it would become what? 0, and this 1 remain as it is. Clear? Okay. So similarly you may check for what? You may check for 1, 0. Because only for 0, 1, 1, 0 we can be able to accept the fact of swap gate. Yes? Otherwise we have no visualization over a swap gate, because 0, 0 would become 0, 0, 1, 1 would become 1, 1. Clear? Should we go ahead? So let's go. So these classical gates, remember these all, okay? Because in code, what we people are going to run, in each code, these will be there. For everything we have written code. Understood? So let's go. This is the Bell state. You people have done it? Bell state already? Okay. Now look. This is the generalized equation in order to write the Bell state. This is the generalized equation. And this is the basic quantum circuit what you have drawn. This is showing the maximally entangled state. Maximally entangled state that creates 0, 0 plus 1, 1 by root 2. But that state is called as phi plus. This state is called as phi plus, 0, 0 plus 1, 1 by root 2. We have its sister state to be called as phi minus, where the minus phase factor is included in 0, 0 minus 1 and 1, 1 state. Okay. Now, if you know the circuit, this is your circuit, okay? You are known, this is the circuit. In order to get this as minus state, what you can do? Circuit needs amendment or not? Don't be worried. Every program is ready for you to run and to visualize by your own. It's now a time to apply your minds, nothing else. What we need? Like Arjun, Only focus on parrot's eye. What we need? This phase factor of minus. How do we get minus as a phase factor? Which gate? Z gate. So we need to append a Z gate. But on which qubit? It's your assignment now. Okay? Now on which qubit? Either qubit 0 or qubit 1. You think. Think. Okay? Now next is psi plus. Psi plus is the another entangled state. And this shows the complement entanglement. Which type of entanglement it is? Complemented entanglement. Means like in a husband-wife relationship what we discussed in the morning session. If husband says yes, wife says no. Yes or no? And vice versa. It happens usually. Yes or no? So such kind of entanglement also be created. This is one of the example of. This is 0, 1 plus 1, 0. This is the complemented entanglement realized over the psi plus state. Understood? So for this purpose, what we need? What is different in 0, 0 and 1, 0, 1, 1? Here, 0 is 0, this 0 becomes 1, this 1 is 1, this 1 becomes 0. So means on second qubit, what do you need? There is no need of controls. If you only apply NOT gate, that would impact. Clear? So on which qubit? Okay. So similarly you think for Z, that is where to apply on Q0 or Q1. Now similarly here, psi minus. What we need? It's the same complemented entanglement state. And what we need to apply here? Minus. So what it needs now? Z gate. Okay. So to apply a Z on Q0, X on Q1, okay, different possible settings of maximally entangled quantum states can be created. Understood or not? Earlier I discussed, what I discussed? The probability amplitude associated to each of the Bell state is what? 1 by root 2. Yes? But I know the fact, over a 2 qubit system, 4 quantum states are actually remains present in a quantum system. 0, 0, 0, 1, 1, 0, 1, 1. But out of these 4, only 2 of them are becoming entangled at a time. But how many different possibilities we created? 4. Still we are running with 4 different possibilities. But at each time, this is not called to be a 2 different state, it's a combined state. Clear my point? It's a combined states. They are not the individual states, they are the combined states, same states. That is why we used to call it as what? Entangled states. Qubits are correlated. Understood? Yes? Should we move? Now, here comes teleportation. Teleportation. Understood? Understood? Or means learned already in the previous lectures? No. Now, you try to understand the technique, what the teleportation is. Now, this should be used in a communication purpose. First, you try to understand. There is one sender, one receiver. I want to send my quantum information. Remember, okay, I want to send what? My quantum information from sender to receiver. So, quantum information should be contained in what? Qubit. Understood? But I do not want to send the physical qubit from sender to receiver. Physically, what the information I have, I do not want it to send to receiver. But what I am interested in? I am interested in to make the exact copy of that quantum state towards the receiver side. Understood or not? Without sending, we are just planning for one of the quantum mechanical phenomena, that the quantum state which is available at the sender side, the same has to be reflected there at where? Receiver side. It has the complex mathematics operations. Circuit is simple. Very simple circuit. If you look at here that left side, you note down by your own. There are 3 wires. Okay? How many wires? 3 wires. So the initial 2 wires, first and second, they belong to sender. You note down. Okay, they belong to what? Sender. And this third wire belongs to what? Receiver. Now, understand. The first wire of the sender, this is the first wire, the first qubit. It has been initialized to psi state. Psi state means it's arbitrary random quantum state. It's a random quantum state where alpha and beta means A and B being a probability amplitude have not been defined yet. I do not know how much is the quantity of alpha, how much is the quantity of beta, because this is one of the special case of non-uniform superposition. There may be non-uniform superposition. Clear? Or there may be a possibility of uniform superposition also, but we do not know. I do not say that A and B cannot be equal. This can be 1 by root 2. Yes or no? But there can be other chances also. But whatever the quantum state of information we have at the sender's first bit, the same quantum information we have to send to the last qubit as the output of this circuit. Now, before discussing with the mathematical facts of this teleportation, look at the last. Look at the last here. This is written as 0, 0, 0, 1, 1, 0, 1, 1. Okay. So these are showing 2 qubits. What they are showing? 2 qubits. Here you look. What 2 qubits we are measuring? Sender's qubit. So these are the outcomes of the sender's qubit. 0, 0, 0, 1, 1, 0 and 1, 1. Means these are showing that the sender is available in either of these quantum states. But whatever the desired information sender is having at the first qubit, at the output of this execution of this circuit, the third qubit, if you see, third qubit, like this, it always remains psi. Psi was what? The quantum state what we prepared. Huh? Yes or no? So now let's come back with a flashback, okay, like in a movie type things. Okay, first we should know, okay, who is Sanjay Singhania, like in movie, do you remember? Acha, but you must have, I think, watched in Telugu. What to say, the Gajni movie, Gajni? Huh? Huh? Sanjay? Acha. Actually, I had no intention to discuss these all things. I saw a few of the faces as sleepy. So when we do like these activities, no, so every sleepy person immediately gets activated. Huh? Kya hua? Like this. No, okay. Look at the board here. So now, what to do first with this circuit? Remember what to do. This is sender's second qubit and receiver's qubit. Initially we made the entanglement of what? Sender and receiver qubit. So for that one we created a Bell state B00. B00 means what? 00 plus 11 by root 2 means they are not having complemented entanglement. They have likely entanglement. कि मैं जो चाहता हूँ means whatever is there in my mind, the same should be reflecting to your mind. This is a kind of entanglement we are creating. Clear? So first we have made the entanglement between a sender and a receiver. Okay? Now, so how do we make this circuit? This part of the circuit is missing here. You know because. What's the part of this circuit? How do we make the entanglement? That is header mart followed by control knot. That's an entanglement. Yes or no? So I have not drawn it. So remember, the first thing is this entanglement should be created among both of them. Followed to that one. Now create an entanglement between a sender information and sender qubit. Clear? Now what I am doing here, that whatever the information we want to send, its reverse entanglement is getting created here from the qubit number 1 to qubit number 2. Okay? After that one, there are two controlled operations. One is looking from the sender, that is second qubit. Second is looking from the sender first qubit, that is control X, control Z. And why and what is the purpose of these operations, you let us know here. This is operational step psi 1. This is psi 1. Okay? We have divided our circuit into multiple circuits. So this is psi 1. At psi 1, what we are doing, this is psi multiplied by B00. Okay? What is B00? What is B00? This is Bell state created among sender and receiver. So now, a psi state is written as A0 plus B1, so it is written. Clear? And Bell state can be written as 00 plus 11 by root 2, written. After that one, we are simplifying these states. Now apply what? Tensor product. It's a tensor product, nothing else. So when you apply the tensor product, so A multiplied by 0, 0, 0. So it is A triple 0 plus A 0 double 1, A 0 double 1 plus B 1 double 0 plus B triple 1 divided by root 2. Now you remember, there are 4 different states with what is the amplitude? 1 by root 2. Can it happen? In a quantum system, the quantum system with 4 different states, but the amplitude to measure each of them is 1 by root 2. Apply modulus square means 1 by 2. If 1 by 2 is a probability associated to each of them, so probability becomes 2. No. So because it is not a complete circuit right now, okay, and we have only done what? The tensor product form, okay. So otherwise we should not take this tensor product. We should separate apart both of these quantum states. Now, up to this operation ready? Clear? I am asking to all. Clear? Sir, at the last. Chalo. Now, psi 2. This is my psi 2. So at the psi 2 state, what do we apply? C0 gate. By taking first qubit as what? Control, and second as target. Okay? So when you see first control, second target, so applying C0, it is written as 1, 2. So 1, 2 stands for 1 is control, 2 is target. And on psi 1 is resulting psi 1 state is this one. So now A triple 0, A 0 double 1, B 1 1 0 and B 1 1 divided by root 2. Okay, so how it is happening? Because we have applied the C0 gate here. So C0 means what? Whenever the first qubit remains in state 1, apply the NOT operation on second qubit. So you look at here. Here, first qubit is not 0, first qubit not 0. Here, this first qubit is 1. So second would become what? 1. So if you see here, it is 1 1 0. Clear? Now here, 1 1 1. So because the first qubit is 1, second is flipped. So it becomes what? 1 0 1 by root 2. Is this clear? Huh? Now listen, next what to do? Apply Hadamard on which? First qubit. So when you apply the Hadamard on the first qubit, so I am taking here, this the Hadamard is applied on the first qubit here, okay. So applying Hadamard on the first qubit means on the, this is the first qubit, here qubit first is 0, qubit first is 0, qubit first is 1 and qubit first is 1. So apply Hadamard on 0 would be 0 plus 1 by root 2. Yes. Again for this one, 0 plus 1 by root 2. For this 0 minus 1 by root 2, and for this 0 minus 1 by root 2. And because 1 by root 2 would be taking as common, okay, so earlier it was 1 by root 2, so 1 by root 2 multiplied by 1 by root 2, it becomes 1 by 2. Clear? So now you have the 4 different possibilities of states with what? 1 by 4 amplitude. Yes or no? We have to transform this state like to teleport our quantum state without sending the physical quantum bit to the receiver side. मतलब समझ रहे हो? Means we are making one mechanism through which we are not sending any physical things to the receiver side, but the receiver is about to know that what the sender is wants to communicate. Okay, this is like to call as a close connections. We used to call when we remember someone who is close to us. So the people may start hiccups. Yes or no? Yes or no? Yes. So it happens. So if it happens, means what? There are some connections, and we people are just making such a connections here. Understood? So now listen. So what's the fact? The fact is, after this state, we want to apply what? Control NOT gate. So in a control NOT gate, the second one is control and third qubit is target. So this C0 is written as 2, 3. Okay? So 2, 3 means second is control, 3 is target, and to be applied on psi 3. Clear? Now with this psi 3, you look, C0 is applied, so always look for second and third. So second and third means this first qubit is remaining same, 0 plus 1, 0 plus 1, 0 minus 1, 0 minus 1. Only check for last 2 qubits. Here second one is 0, leave it. This is 1, okay. So because of this 1, the second would be flipped. Yes or no? Second would be flipped or not? Now after that one, this is 1, 1. So because the first qubit is 1, the second one should be flipped. It would become 0. No, 0. Where? It is 1, na madam? Achha, now for before state, okay, we people have done, okay. So it is 1, 0. So from 1, 0 it is becoming 1, 1. Okay, it is 1, 1. And now there is no impact on this one. So once you reach to this state, now we are just performing this tensor product operation on the entire states. So if all such states are tensor with each other, so it is becoming 0, 0, 0, 1, 0, 0, like 0, 1, 0, 1, 0, 0, and like this. But we have two states like this, minus of B of 1, 1, 1 and minus of B of 1, 0, 1. Yes or no? Only two of states are there whose phase factor is included with minus. Clear? Now, last operation is what? Control Z. So control Z means the first qubit should be control and the third one would be target. So by taking 1 and 3 as control and target on psi 4, so if you see, so only observe the first qubit and last qubit. Whenever your first qubit is in state 1, okay, whenever your first qubit in state 1 and your target qubit is also in state 1, then only the phase would be inverted, because Z operation have no impact on control, on 0 initialized quantum state. Okay, so like you see, first is not control, no such control because it is 0, leave it. This is 1, but what about this last? So there is no impact, so we are not considering. Now look at third, no problem, means leave it. Here this is 1, but the last qubit is 0, so no need to apply. Clear? Now next, this is 0, so not applied. Here this is 1, clear? Like in the above statement, here you check, this is 1 and the target qubit is already 1. So at that time, Z phase factor would be involved here and this minus would become plus. Understood? Similarly, here no operation and here 1 0 1 means this is 1, last one is 1, so at this time also again this minus would become plus. Okay. Now, after getting this one, we are applying this measurement operation. And after just applying these measurement operations, we are getting these resultants. Okay. Because initial 2 qubits have been separated out with 0 0 0 1 1 0 and 1 1. Understood? And the last qubit is remaining in a quantum state, what we wanted to send. So what happened here? I wanted to send some information from sender to receiver. Understood? So in order to send such a information, I did not send any physical information. Rather, the same information what I wanted to communicate, the information has been teleported. This is to be called as teleportation. And here, if you observe, the 0 0 0 1 1 0 and 1 1, they must be the quantum states. What they must be? The quantum states. So for the quantum states, they have their probability distributions. Yes or no? What are the distributions? By root 1 by 2. 1 by 2 means applying modulus square, it is 1 by 4. So with 1 by 4 probability, there is a significant outcome that have been reached to the physical, that is receiver side, that either of these states can lead you to measure the result as what? That is the quantum state that I wanted to teleport. किसी भी एंगल से देख लो, information पहुंच गई. Understood or not? Are yes or no? So we will have such a demonstration again. Okay? Now look at here. What's the time like? 3:25. अभी तो बहुत टाइम है, 1 घंटे में तो बहुत कर दूंगा. चलो look. Ma'am, if it is possible to ask somebody to serve the tea here, is it possible? No. No, I am asking only. Otherwise, if no such permissions are there, so, huh? No, I have no objection if they have a tea here itself. Huh? Otherwise, need to ask them. Thank you. Sorry, but actually I can't help it. Right now already our that is train got delayed. Okay, and we have to make up. Clear? So now look at here. So this is the Deuce algorithm. You people have learned it, Deuce algorithm. That is to demonstrate. What to demonstrate? That is the quantum parallelism. Quantum parallelism. In order to check whether your function is a balanced function or a constant function over a single qubit system. This is possible because for a classical way you have to execute 2 number of queries. It's a query algorithm. So in a classical way the 2 queries have to be passed to an oracle in order to check whether your given function is a balanced function or a constant function. But in a quantum mechanical settings, like to utilize the quantum parallelism, this is the first quantum algorithm that demonstrated the quantum parallelism. Okay, so because of this setting, this is the simple setting. One qubit is initialized to 0, other is initialized to 1, apply Hadamard both of them, this unitary function transformation. This unitary function transformation should take what? The values of x XOR with y. Understood or not? And based on that one, after that one, the initial qubit to be supplied as again Hadamard followed by measurement, so you will get what? It's okay, it's okay. I told madam, so we take otherwise. So understood this one? Yes. So I think you remember the circuit, because if yesterday only you have learned these facts, so I think you should remember. Clear? So this is all about whether the function is constant. So if the function is constant, means function of 0, function of 1 always result the same value, okay, irrespective of the inputs. But if the inputs are assigned, okay, like f of x, for a balanced case the function of 0 should not be equal to function of 1, because if for the first input, if you are receiving 1, means at the second there is a definite 0, because it's a completely balanced function. Understood? Clear? Huh? Now we have reached to our goal point. This is the demonstration of everything using Qiskit programs and Quirk simulation. So this is very fast simulation. In within a 1 or 2 minutes I will let you know everything. Huh? Chalo. Let's have a tea break. Go fast, come fast. Because the lecture is scheduled up to, madam, 4:20. So 20 means you should come fast.
5 minutes only, please.
Please cooperate. पानी पी ले यार. पानी पी लिया मैं, चाय पी के आएंगे. चलिए आप पिएंगे चाय? चलिए. हाँ, यहीं पे आ जाएगा. चलो ठीक है, तो यहीं बैठ जाते हैं. ठीक है, थैंक यू. डन। यार एक ये वाली और लाइट बंद कर दो तो मेरी आंखों पे भी नहीं आएगी, ये वाली कर दो आगे बंद तो ये शायद दिख जाएगा ये। अरे तुम रिकॉर्डिंग में ठीक है, चलो इट्स ओके। Now listen how to code. Look, this is importing of libraries first. To write any quantum program, earlier in the last session somebody is having doubt, the done PhD, where is the candidate? Like no, some other person now who was saying that we cannot be able to simulate, I think madam, yes, now recognized. Now listen, so some settings I am letting you know, okay, based on such circuit settings or the program settings, you make it as just a model, okay, in between you just fix your code, okay. So this is just a template, so you use this template and just fix your code in between and done, understood. So only you will have to work for your logic. Now listen, what this is the Qiskit, PIP install Qiskit. You have done with the installation of Qiskit, clear. So Qiskit package have already been installed with certain version numbers, okay, like 1.3.0 I asked you to install, you people have installed, okay. So now from this Qiskit package we are importing what? This is a quantum circuit. Basically this quantum circuit is a class, okay. This quantum circuit, because as per the naming convention, nothing, there is no rocket science here, simple thing to understand, this is what? A quantum circuit, multi-word names, yes, started with the capital letters, clear. So it's a class, okay, class that is imported from the Qiskit package, understood. Why this class is needed? In order to create the object. Listen, we need to create the instance of the quantum circuit. Instance means object, okay, and every object would be a dynamic one here. So now from this quantum circuit we will be creating one quantum circuit object, okay. Now look at here, this is written as QC. QC is the name of instance, that is an object created based on what? Quantum circuit. This quantum circuit is here, class, constructor called, yes. So the constructor is called here with some arguments, okay, arguments to be passed to in the parameters, okay. Now so now what this first argument is specifying, this specifies the number of qubits, second this specifies the number of classical bits, understood. So the number of qubits and number of classical bits we need to specify, understood. So the simple fact is there, whatever the number of, like for teleportation circuit, how many qubits we need? 3. And how many we are measuring? Sender qubits, yes. So if we were measuring sender qubits, so we need 2 classical bits. So it does not mean here to be like the number of qubits and number of classical bits to be taken always same, it's up to you, okay, how many number of qubits you are supposed to observe, clear my point. So here I am interested to have a 1 qubit with 1 classical bit, that is to be observed. Now I already told you what about the transpile, what the transpile does, it loads your quantum circuit onto the back-end simulator for optimization tasks, clear or not. So now listen, this is the transpile and this is still the method which has been imported from the Qiskit package, understood. Now this is Qiskit _air, I told madam, that is hyphen used while that is installing, but here underscore is written, clear. So now this Qiskit air, from Qiskit air we are importing air simulator where air, अरे क्या हो गया इसको, क्या हो गया यहाँ पे, क्या हो गया ये, लैपटॉप की स्क्रीन यही थी. चलो, look at here. So air simulator is what? Is my back end. So transpile, the task of the transpile is what? To load the instance of this quantum circuit onto the instance of the air simulator. Clear? So if you see here, this piece, this is a simulator, this is object which has been created on constructor basis. This is default constructor. Okay, not only default, we have, this is default argument constructor. Basically you may pass the argument also, certain arguments can be passed. Okay, you may set your vectors. Okay, but here in default we have taken, so this based on air simulator, this object has been created. Clear? And this transpile task is what? To load this quantum circuit QC onto what? Simulator. So if you see here, this is the transpile code. Can you be able to see? Transpile is doing what? It is taking two parameters. First is QC, second is simulator. So it is loading this quantum circuit instance onto the simulator. Clear? Is it clear? Now come on to the importing of libraries. So from Qiskit visualization, because visualization we have separately installed for the visualization purpose, because everything needs to be displayed in the terms of histograms. Okay, we need to plot because the model is probabilistic model. So anyways we will have to see that what are the end outcomes are generating by the machine. So now look at here. So from visualization we are importing what? Plot of histogram. So with the basis of that one we will be plotting the histogram. Clear? Now, and the matplotlib, so we have already taken for. Okay, so now this quantum circuit is already created. Now what we did? QC is the instance of the object, instance of the class, dot access specifier. Okay, that is giving the access to the particular gate. This is header mod, and in parameter to header mod we pass the index of the qubit. You just note this thing. On any gate we are passing what? Index position of the qubit. So this 0 is specifying what? On 0 index qubit we are applying the header mod on the QC. So QC would be a circuit. On that circuit there would be one header mod on the 0th index qubit. Clear? Now after that one, all remaining codes have been disabled. Okay, because it has been made as comment. Now this is QC dot Bather. So now the quantum circuit is about to Bather. So now the list based processing can be there. Okay, now this first index is showing this is the 0 index qubit to be measured in 0 index classical bit. Is it clear? 0 index qubit to be measured in 0 index classical bit. Like for multi-qubit system also, like this has been already there in comments. You have the code, you may run by your own at your home, just try to practice. Okay, so the list of numbers you may also, list of indices you also pass, like measure 0, 1. It means index 0 and index 1 of the qubits would be measured in index 0 and index 1 of classical bit. Is it clear? Now this is the finalized code, madam. You just see, this is what? Here a code that to be taken as a template, because you feel that errors are keep coming now. So just look at here. That is the simulator, the instance is created. After that one, compiled circuit. Basically it is an image, that is an object image. What we people are, that is a binary image of the circuit that has been created. Okay, after the execution of that transpile. So now after that one, when this circuit is created, it is assigned to the compiled circuit, and now the compiled circuit would be passed in a run method. So run is a method that is being called with the simulator. Okay, simulator is what? This is a instance of air simulator class. So this dot run method is again basically it is that is one of the static method assigned here in which one? That is in air simulator. Sorry, ये क्या हो गया यार? लैपटॉप जा रहा है. चलो, done. Now look. So now after that one, the simulator dot run, we are just running this compiled circuit, and within that run method we can apply this comma here and put down our shorts, that is shorts of execution. If you are omitting this parameter, so by default the number of shorts taken by the Qiskit framework is 1024. Clear? So for 1024 time it runs your code. Understood? Now after that one, dot results. So now after just running that circuit, whatever the results are there, that result will be stored in a result variable. Okay? And from that variable, that is every time, because the result would be there, we take the counts, that how many number of times your zeros or ones or other quantum states you got measured. Okay? And this is to be assigned in a counts. Okay? And you do not just assume like there should be a loop, like 1024 times we should run a variable like from I equal to 0, I assigns the value 0 to 1023, and in that one the count should be updated like, है ना? If you are thinking like in a manner, means you are just going in a wrong direction. It is a completely parallel system. Okay, so it's an intrinsic parallelization of the quantum machine. There is no such looping aspects. Everything is happening in parallel. Understood? So 1024 instances are doing. Understood or not? And every corresponding outcome is being measured here. Understood? Now after that one, the print, the counts to be printed here, this is the QC.draw. So the quantum circuit draw is a method, and within that argument we have to pass it MPL, that is matplotlib, in order to have the graphical outputs. After that one, the histograms to be printed. Okay, so now let me just run this circuit. The same circuit we will be running over the different platforms. Clear? Madam, still we have time? Hey, time? Acha, it's okay. 420 na? 420. Let it set up. Now, you see, you all have got the same? Yes? Now understood with the interpretation of the code? Okay? It's a simple code. What we should remember, the first, the importing of quantum circuit, that is the first thing. Second, the importing of what? AR simulator. These are the requisite things. Importing of what? Matplotlib, because of plotting of the histograms. These three things are requisite always. Clear my point or no? And that is simulator, that is AR simulator. Clear? Now, if you see the number of times, it is showing 515, 509. Agree? Now let me run it again. 515, 509. 504, 520. But you observed, exactly 2 times it gave the same result. Yes or no? But now the result changed. Now, changing, changing, changing. So means what? It's a completely random outcome. Understood? So it may happen always within the quantum system. Clear? Now, but this is simulation. Okay, let's run another circuit. The circuit was what? Entanglement. This I already show you. Okay, shown you. This is import star. If you do not know anything what to import, so it's better to import all. Yes or no? Import entire package. But it is redundant. The things have redundantly used here. Okay, because here the import star was already sufficient to import everything. But again, the import quantum circuit I used, Qiskit, from Qiskit AR, import AR simulator, that was used. Okay. Now from visualization, plotting of histogram and matplotlib again in an inline person we have taken. Now if you run, let me just clear output first. Okay. This is the quantum circuit for entanglement. How many qubits and classical bit we need? 2 qubits, 2 classical bits we need to observe. This is the QC dot draw. So let's run cell by cell. So let's run it. The first one. First cell successfully executed, importing of library done. Now second, okay, let's check whether this has been created. Yes, but we have not appended any of the quantum gates on the circuit till now. Clear? Now next, on circuit, because circuit is an instance, on circuit we are applying Hadamard on the 0th index qubit, okay, and we are plotting it through the matplotlib. So means this time you will expect the graphical output. Understood? If you omit the matplotlib, so you will not get, you will get the circuit like this, okay, in an analog form. Now next, what to do? This is circuit.cx. So cx stands for controlled NOT gate, okay, cx stands for controlled NOT gate. Like similarly we have one extended gate like ccx. So for ccx it is ccx. So here in control NOT, 2 parameters. First is showing control qubit, second is showing target qubit. In ccx there would be 3 parameters. First 2 would be control, third would be target. Similarly we have one special gate which is being provided by Qiskit programming framework, that is called as multi-control NOT gate. What to call? Multi-control. There would be multiple controls, like suppose I am dealing with n number of qubits. So n minus 1 can become a control. There is no such restriction. Yes or no? And the final one would be the target one. And why we need it? And why I am discussing, there should be a reason. Okay. When we realize our Grover's algorithm, okay. So in Grover's algorithm I will let you know that this multi-control NOT gate would work at all. Okay, I will let you know. So now next. So this has been applied. After applying C NOT gate, measurement 0 and 1 qubit to be measured at 0 1, followed by matplotlib. So again let's check. So it is an entanglement circuit created. After that one, this is the same settings, need not to be discussed at all because this is a template based code. Okay, it saves our time. Understood? Shall we move? Okay, let's learn this one. This is the plotting of histogram. 524, 476. Let me run again. That's it. Over. These are the 2 simple demonstrations. Understood? Now let's have a similar demonstration. Have you run your code on the Google Colab? Similarly the same, the Qiskit install, that is PIP install Qiskit, visualization Qiskit, that is AIR. Okay, by just installing or prepare your own platform, you may run the same code by taking the copy, paste it there, run your circuit. Understood? Okay, so so because look at here, if it is 1000 times, so look at here, in a run method I told you, no, the second parameter can be shorts. So shorts will define what? The number of times the same circuit to be executed on the quantum machine. Understood? So if the same circuit to be executed on the quantum machine, so the shorts is up to you. If you do not set it, like in the previous program we did not set, we omit that argument. So because of that one, 1024 was by default taken. Clear? And it usually happen at the real machine also. Clear? Now, before proceeding to our next course, first you look for the Bell state realizations. Because right now, just now we have just already checked about. Now look, these are the importing of libraries. Okay. So importing of libraries, and these are to show the state vector. Okay. That is, state vector means what the quantum state vector is there. Okay. So after that one, look, this is the plot, a block multivector. So the multivector means your Qiskit vector can be plotted onto the block sphere again. Okay. Now before that one, if you see this circuit is realizing what? 0 0 plus 1 1 by root 2, for which we have already checked the code. So for that one, 2 qubit and 2 classical bit of circuit we are taking, followed by on 0th we are applying Hadamard, control 0 and 1 applied, measured, and this should be the output. So let's check, because why to waste the time in that one? Okay, there is no need to waste the time. Already discussed this code. This code is same, already we discussed. Interested in other different possibilities of phi plus, phi minus, psi plus, psi minus. So what I told you about 0 0 minus 1 1 by root 2, what to apply? What to apply? Z, yes or no? So you check it here. 0th index Hadamard, now control qubit, okay, that is a control knot, followed by on 0 itself apply the Z gate. So once you just realize this one, you check, this is your quantum circuit. Clear? And this quantum circuit ensures that you are realizing a quantum state phi minus 0 0 minus 1 1 by root 2. And there is no impact, whether it is 0 0 plus 1 1 by root 2 or 0 0 minus 1 1 by root 2, because still the states would be same. Understood or not? And they will be measured with the same possibility. Only the difference is what? Phase factor. Phase factor. And there is no changes if you include the phase factors. Clear or not? Now, third one is, this one is to run that circuit. Now look, 0 0 1 1. So still the states are same, na? States are same, 0 0 and 1 1, and we are running these states. Now next is Bell state realization for 0 1 and 1 0. For 0 1 1 0, what to do? Hadamard and C naught are same. Next is what? Apply X gate on the first index qubit. We already discussed. Clear? So let's run this code. This is the code. Clear? And when you just simulate with the coins, 0 1 and 1 0, these are the other two possible states which are being measured here. Okay? So these states are available to you with almost, because if we run the same experiment multiple times, every time we will be expecting different possible outputs. Clear? Now this is the last, 0 1 minus 1 0. What should be the circuit setting? Apply Z gate again to the already existing circuit of that is psi plus state. Okay. So at the psi plus state, here you look, H0, control knot, X1 and G1. Clear? This is the requisite circuit. And after running that one, let me run this circuit. Now this is 0 1 1 0. Okay. So this is a simple demonstration related to what? This is what? To the Bell states. Okay. These are the simple demonstration to be taken. Okay. Now let's proceed, because now 4 o'clock. I need to cover at least the significant part first. Okay. You should be able to visualize what we people are doing. Okay. You try to understand. We have done with teleportation. We have the code for teleportation also. But if we discuss the same code, it may take time. But hardly in 1 minute of time I may be able to demonstrate you how the teleportation can be done. You just look at here. What I am doing, I am taking here this internet not connected. Do we have password, madam? This one? Let's check. Okay, so on Google itself, write down Quirk simulator. QUIRK. You have your own machines, okay? And even on mobile phones also you may work on this. Okay? So it's a toy now to play for. Now, in a Quirk simulation, I am just clicking on the first link. You will get the first link of algazar.com. Okay? So the people have given us a very good simulator to simulate now. Okay? Look, I am applying on edit circuit. Okay? After that one, you remember the teleportation circuit? What was the circuit? Sender and receiver, bell states, followed by reverse circuit of the bell state, means C0 followed by Hadamard, and then first qubit would be controlled by naught. Second qubit would be controlled by naught, and from first qubit control Z. Okay, followed by two measurement. Now look at here. It's a simple, very simple approach to observe here. Look at here. Here you have the drag and drop options. Whatever the gates you learn, okay, all such gates are available with all such kinds of information. This is really a good tool, okay, but not acceptable in that is a paper writing, because it's only for that is a gaming purpose. Okay, but if you include, means the people do not appreciate, and the people need the code from Qiskit only. Okay, some standard framework should be there, so they expectation but leads to disappointment at all. So it's okay. So now, so the thing is that we need 3 qubit. So for 3 qubit, first we need to create what? Entanglement between a sender and receiver. So what I am taking, I am just dragging this Hadamard gate and putting it to the second qubit. Still the third qubit is not there. But if I need the third qubit, so now what to do? This is the control. This solid bubble is showing a control 1. And this is why I usually suggest this as a good simulator to the people to try to understand. Qiskit would not directly allow you to take a quantum state 0 as a control. Qiskit means quantum state 1 control qubit. Why always quantum state 1 to be a control qubit? If I am interested in my circuit, I want to make a 0 as a control qubit and I want to perform certain operation, then I should be able to take. So here, if you see this, this solid bubble is showing that control qubit is selected as 1. And this hollow bubble is selected, means it is showing that control qubit is available in quantum state 0. Understood? Clear? Now, before that one, so what to do? Bell state creation. You take that control, and this is not. Look, only the drag drop. I have taken this knot and applied just beneath the control qubit. Now, this is the bell state created. Bell state created. If you see this, there is a 50-50% chance, because this part of the circuit is showing what? 0, 0 plus 1, 1 by root 2. Yes or no? So here if you see, there is what? 50-50% chance of measuring your answer. And if you see, here is a block sphere. Yes or no? This is the block sphere. Okay. Now, here, your information what you are interested to send, that is the first qubit, is initialized to what? 0. Means I am interested to send what? 0 initially. Means the same 0 should be there at the receiver side. Now look, after that one, what to do? What to do? That is control not followed by Hadamard. Yes, control not followed by Hadamard. It's a reverse entanglement we have created. Yes or no? As per the circuit. Now you know the mathematics. How that is the quantum state have been transformed. Clear? Now listen. After that one, what to take? On the second qubit, apply what? Not. And on the first qubit, apply what? Control Z operation. After applying these operations, can you be able to see whatever the quantum state I have here, 0, the 0 is reached to the third qubit or not? Or can you be able to see? Huh? 0 has been reached, but we have not done the measurement. So for measurement, you take this measurement operations, apply here. These are the measurement operations. After applying the measurement operation, still there is no impact because my quantum state that I wanted to teleport, it has been teleported. What the state is? That is 0. Now, the circuit is ready, only the inputs to change. Now let's check. Here, you have the privilege to click on this quantum state. If I click, it becomes 1. You see the impact. Can you be able to see the impact? This is the teleportation circuit. It guarantees that if I had one to teleport, so one has been teleported. You see the third qubit is on. Okay, let's move on. Now again I am clicking on. This is plus. Plus means 50% chance either to have 0 or to have 1. So now if you can see here, there is a 50% chance available on the third qubit. Are yes or no? Means your quantum state have been teleported anyways. Understood or not? So just by updating the input settings, you can be able to realize the corresponding outputs. Clear? Is this clear? Okay. Now before this is one of the demonstration. Now this tool you remember, and you may do your own work directly for using this tool. Okay, so this is for your satisfaction purpose, because if you see the bigger quantum gates like quantum Fourier transform, inverse Fourier transform, these have already been created in the simulator already, because otherwise each topic is a separate topic and it takes around 3 to 4 hours of time to discuss separately. That is for the concept of quantum Fourier transform and inverse Fourier transform. Understood? Now, understood with this? Yes? Now let's move. Still we are left with 8 minutes of time. Okay? So now, write down what? IBM Qiskit Composer. Okay? So when you write down here IBM Qiskit Composer, so you will have the direct link. Always you will find the top link to create your composer. But if you open this composer link directly, so you will not be able to execute your code or your circuit at the back end, because that needs the account. Okay, that needs account to be verified. So if the accounts needs to be verified here, so let me just sign in. Okay, so I have several sign in accounts. So out of them, one of them I will be using here. Okay, so let me just now let me make you all familiar with the IBM platform first. Okay, it's a simple platform, nothing to be worried about. Just look at here. Now I am in. Okay, I have already logged in, because setup and run, this button is active. This button is active. But before proceeding to any of these, I am just clicking on these dots. Okay, on the rightmost dots, and here I am checking the platforms, documentation and learning. There are the 3 categories. Okay, First I am just clicking on platforms. So these are the IBM quantum platforms. Okay, so these are some IBM quantum platforms which is showing here, like is open plan. With this account I have open plan of how many minutes? 10 minutes. It's a free subscription. Clear? After that one, 9 seconds I have used this month. Okay, only I use this one as to demonstrate. Hai na? So now 9 minutes 51 seconds is remaining. Okay. Now if we check for here, that is on the top of the menu options, if you click on the compute resources. So these are the several available compute resources which are available on the cloud platform, and every machine is given with the logical name. Can you be able to see? Okay, every machine is already assigned with the logical name, like this is Brisbane, this is Sherbrooke. Okay, these 2-3 would be direct, like Kingston. Okay, these 2-3 backends would be always provided to you for that is for your free subscription. Clear? So how to read these? If you see 127 qubit machine, 133 qubit machine, as well as 156 qubit of machine, all different types of machines are available because this is free plan. If you have a subscription by paying 8 lakhs rupees for 1 hour, so you will have 1000 qubit of machine for your subscription also. Okay, and for that one they will provide you the complex simulation of the entire Hilbert space for all the quantum states. Clear? Now before that one, now we should go to dashboard. These are some tasks that have been earlier executed. Okay, now you come down to again and click on learning. This is how you should proceed. Click on learning here. Now after learning, there are 3 menu options here: home, catalog and composer. So otherwise you have the direct option, directly type on Google, log into the composer and directly work on it. Now click on composer. Still 5 minutes left. Okay, just wait. So now this is one of the demonstration to you. I have used how many qubits here? Look, 0, 1, 2, 3, 4, 5, 6, 7 means 8 qubits. Okay, from 0 to 7, 8 qubits. In these 8 qubits, I have applied the same operations. It is basically called to be a GHZ state. Greenberger, Hellinger and Zorne state. It's an extended state of a Bell state. Bell state is a maximally entangled state over a 2 qubit. It is a maximally entangled state over a n number of qubits, where one of the qubit remains entangled with all. Understood this point or not? Huh? Now, so because of these number of qubits, the probabilities and their state vectors are not shown. Now what to do? I am clicking on the qubits, okay, deleting, clicking on deleting, clicking on deleting, again delete. Now how many qubits? 6. So means up to 6 qubits the Qiskit framework is allowing you to visualize. Okay, now these are the state vectors, these are the probabilities. Understood? Now here the probability and the quantum sphere, we have 2 options. If you just click on here, so still the quantum sphere is not available. So again you delete. So now for 5 qubits it is allowing you to have your quantum sphere visualization. Understood? Now after that one, if you see here on the right hand side, these are the state vectors over 5 qubit. 5 qubit means 2 raised to the power 5, 32 combinations, all are available in the form of quantum states, and among all of them 0 have been default initialized. Can you be able to see? 0 is initialized by default, means every qubit is remaining present in the 0 quantum state. Clear? Now let me just delete. Okay. Now delete this one also. Now if I have what? 1 qubit, so I do not need 10 number of classical bits. This is showing C10. C10 stands for classical bits. Now minus, 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 apply minus several times. We have to apply. This is just one of the time consuming factor here in Qiskit. They have not made a very familiar framework. Okay. Time is, madam, still 3 minutes. Now look. So for a single qubit, by default, the qubit is available at 0. Now I am applying this Hadamard. Okay. Here you can have the option in order to place your component free from alignment, left alignment or layered alignment. So I have initialized it to free from alignment. Wherever I want, I should place. Clear my point? Otherwise the circuit does not look like good. Okay. So once I applied this Hadamard on this one, you may see that 0 and 1 both are simultaneously present or not. Clear? Now you see on the probabilities. What are the probabilities it is showing? 50%. It is a modulus square. It's a modulus square of what? These are the amplitudes. Amplitude is what? 0.701, 707. It is 1 by root 2 only. So when you have 1 by root 2, applying modulus square, you will get the same resulting probability. Clear? Now, after this Hadamard, what to do? Apply this measurement operator. So once you apply this measurement operator, your quantum bit would be measured in any one of the quantum state, either 0 or 1. Got my point? Now what to do? After creating this small circuit, you just click on setup and run. Go. Now how many options I have? 2. These are 2 options. Which one? Sherbrooke or Brisbane. These are the logical names of the quantum processors. Okay. Only 2 options. But we have already checked that the several compute resources are available at the back end, but only they are allowing us to have these 2. Now in this one, the QPU status, that is quantum processing unit status, is available as online. Yes. The total pending jobs is showing as 4, and in that is the below one is 25. Now this is showing qubits that is supported by this processor, that is 127, 127. Clear? Both are equally capable processors. This is showing as the error rate. What it is showing? That is the expectation of errors. If you see, it is very small values. Okay. It is very small values. If you prefer based on the error rates, so what or which one should I go for preferring? 1.48. Okay, that is least error. But there would be no such impact. Clear or not? Because marginal errors are there and it would always remain. The people are working hard to have a noise-free quantum system, but still we are in the era of noisy intermediate scale quantum systems. Okay, our quantum systems are always a noise consuming systems. Clear my point? Now, after that one, this CLOP, like flops, we used to take this as a unit for supercomputer processing. Okay, floating points operations per second. Okay, now here we use CLOPS, means circuit layer operations per second. What to call? Circuit layer operations per second, means how many circuit layers will be processed per second of time. Understood or not? Huh? So based on this circuit layer operations per second, we can what? Execute our circuit. So the task, so this machine means the below machine is enough capable. 180K. Okay, so 180K clocks it can run 1 second of time. So I told already, it may happen that your quantum circuit is in a queue, in a job queue on a cloud platform for 10 minutes, 20 minutes, half hour of time, because simultaneously throughout the world several requests are coming to the single server. Understood? And after receiving the multiple processing requests from the different clients, okay, it has to be there in the queuing mechanism. Okay, but anyways, once you get the chance to run on the CPU, like in an operating system concept, it takes only the quantum of time. That is in a round robin concept what we used to call it. Yes or no? So only the quantum of time it takes in order to run the entire circuit. Clear? So now after that one, let's select which one to select. Okay, default selected. Now you click on the run. This is the last one. I've made 1 minute extended. 1 minute extended. Okay, it's okay. Now you see here, it is showing what? Running. Means it has not been assigned to the quantum processor. Once it has been assigned, you look. This button is active and the job is sent here. Job is sent here. Okay, this is the composer job. If you click on here, so you see this composer job, June 13, 4:26 p.m. right now. Okay. Now, this job has been completed. And job is completed and this is showing the frequency of 526, 498. But this is one time execution of this circuit, and by default how many shots they have run? 1024. Now you have the task. You just create, go to your home, create your login accounts, create an entanglement circuit. Simply set up that circuit, let it run. Check whether the thing what I discussed in that is PPT, okay, like we can have the unintentional results like in a manner. Like this, okay, are you getting such a results or not? You just observe this thing, okay. So come up with fresh mind, morning, tomorrow sharp 9:30 ma'am or 9:15 can we early? 9? Chalo, it's okay, 9:30 onward, but the pace will remain same, okay, because I can't help it. Anyways, but you need not to worry. And I am here. If you have no option, no problem, so I can extend my class up to 8 o'clock evening.
Thank you, sir, for your today's session. It is very informative and very much encouraging. And we are waiting for tomorrow's session with more knowledge, insights on quantum programming by Dr. Soni.
Okay. Thank you, ma'am. So tomorrow be sharp at 9:30, है ना? I'll reach definitely.
Thank you, sir. Thank you, sir.
9:30 sir, sharp 9:30.
Should I remove it? Huh?
All the faculty are rushing.
Actually, most of the college buses will reach here by 9:20.
Transport is somewhat difficult here.
It's a matter of transportation. The faculty members are from different places. They are from
So
Kakinada.
at least try to come for 9:30.
Yes, sir. We will be there.
ये किस चीज के लिए था?
15 is not possible. This one.
अच्छा ये इसका था? वही तो मैं I will share not the PPTs I will not share, but the codes I will share. Codes तो I will share, because how would you otherwise get to know, है ना? आपका था है? अच्छा हाँ yes हाँ yes good.
So, and in that there are two machines like sender and receiver. The key is transmitted like in the wave motion as you told. But two panels are there.
Like a wave motion or like a polarization of photon?
As you told in a motion like
Photons are transmitted
yeah,
basically.
photons, yes, yes,
Huh,
yes.
photons
Quantum
transmitted.
plates are there also,
Ah,
sender and receiver.
splitters.
Yes, that is on what we call
Beam splitters.
rectangle basis and diagonal basis.
Rectangular basis or rectilinear basis and diagonal basis.
The same plates are at the receiver side, but now what is the difference between QML and QKD in a single line?
No, both are different concepts.